Now we want to look at absolute extrema. An absolute minimum occurs when the function has no other points in its entire domain where the value is smaller. An absolute maximum occurs when a function has no other points in its entire domain where the function value is larger. If f of xy is less than or equal to f of ab for all xy in the domain of f, then f has an absolute maximum at the point AB. If f of xy is greater than or equal to f of ab for all xy in the domain of f, then f has an absolute minimum value at the point AB. Absolute maximum and absolute minimum values on a closed bounded set R will occur in one of two ways. They may be local minimum or maximum values at interior critical points of R, or they may occur at the boundary of R. We need a process for finding absolute extrema on a closed bounded set. If we let f be continuous on a closed bounded set R in R2, in order to find the absolute maximum and minimum values of f on R, we first need to determine the values of f at all critical points in the bounded region R. Then we want to find the maximum and minimum values of f on the boundary of R, and then I want to find the largest function value that was identified in steps 1 and 2, which will give me the absolute maximum values of f on R, and then I want to find the smallest function value that's identified in steps 1 and 2, and that will give me the absolute minimum value of f on R. So let's work an example. I want to find absolute maximum and minimum values for the function given by f of xy is equal to x squared plus y squared minus 2x minus 2y in the region defined by a triangle that has vertices at the points 0, 0, 2, 0, and 0, 2. The first thing I want to do is identify critical values inside the boundary. I want to take the partial derivative of f with respect to x and with respect to y. Fx is equal to 2x minus 2, fy is equal to 2y minus 2. If I set fx equal to 0, I get 2x minus 2 is equal to 0, or x is equal to 1. Setting fy equal to 0, I get 2y minus 2 is equal to 0, or y is equal to 1. This means that I only have one critical point, and it is at 1, 1, and this lies on the boundary. There are no critical points inside this boundary region. The sides of the triangle are the boundaries that we need to test. These sides are identified by the lines y is equal to 0, x is equal to 0, and y is equal to 2 minus x. On the boundary y is equal to 0, my region runs from 0 to 2 in x. F of x0 gives me x squared minus 2x. If I complete the square, I get the quantity x minus 1 squared minus 1, which has extreme values of -1 and 0 on the interval from 0 to 2. On the line x equals 0, my y values run from 0 to 2. F of 0y gives me y squared minus 2y. Again, completing the square gives me y minus 1 quantity squared minus 1. This gives me extreme values of -1 and 0 on the interval from 0 to 2 in y. On the line y is equal to 2 minus x, x runs from 0 to 2. F at x and 2 minus x gives me x squared plus 2 minus x quantity squared minus 2x minus 2 times 2 minus x. This reduces to 2x squared minus 4x. Again, completing the square gives me 2 times the quantity x minus 1 squared minus 2. This has extreme values of 0 and -2 on the interval from 0 to 2. This means that the absolute maximum value of f on R is 0, and an absolute minimum value of f on R exists at -2. Now, we don't have a really nice, convenient step-by-step process for finding absolute extrema on open or unbounded sets. This is on open domains such as R is equal to the set of all xy such that f of xy is less than some constant c, or on an unbounded domain, for example, if my region R is a set of all xy such that x is greater than 0 and y is greater than 0. In cases like this, we need to use some creativity. We want to keep in mind that absolute extrema may not even exist for our function on these types of domains. So let's work an example. If possible, we want to find the absolute maximum and minimum values for the following function, f of xy is equal to x plus 3y, on the set for the region R given by all xy such that the absolute value of x is less than 1 and the absolute value of y is less than 2. Our region forces our variables to take on a limited set of values. My values for x will lie between -1 and 1, and my values for y will lie between -2 and 2. So I'm going to examine f of -1, -2, which is equal to -1 plus 3 times -2, or -7. And then I'm going to look at f of 1, 2, which gives me 1 plus 3 times 2, which is equal to 7. This tells me that on my region, the function takes on all values between -7 and 7. This means I won't have any absolute extrema for this function on this particular unbounded region. I want to work one more example. I have a rectangular box with a volume of 10 cubic meters and it is made out of two materials. The material for the top and bottom of the box costs $10 per square meter and the material for the sides of the box costs $1 per square meter. I want to know the dimensions of the box that will minimize the cost of this box. I'm going to set up a sketch where I have a box located with a vertex at the origin of a three-dimensional coordinate system so that I can visualize what is happening. Now I'm going to let x and y be greater than 0, and these will be the dimensions of the base of the box. And we're going to let z be greater than 0, and that will be the height of my box. The volume will be x times y times z is equal to 10. I can solve this for z, and I get z is equal to 10 divided by xy. Using this ratio for z, I know that my total cost of the box will be given by c is equal to 2 times $10 times the xy area, plus 2 times $1 times the xz area, plus 2 times $1 times the yz area. This means that my total cost is given by 20xy plus 2xz plus 2yz. Now using the value that I got for z gives me c is equal to 20xy plus 20 over y plus 20 over x. The partial of c with respect to x is 20y minus 20 over x squared. And the partial of c with respect to y gives me 20x minus 20 over y squared. Setting those equal to 0 gives me 20y minus 20 over x squared is equal to 0, and 20x minus 20 over y squared is equal to 0. This implies that x squared times y has to equal y squared times x, and both of them have to equal 1. The only values that work here are for x and y to both be equal to 1. And if that's true, my z has got to be 10, so that my one critical point is at the point 1, 1, 10. Now I need to check the boundaries, and we see that my cost goes to 0 as the point xy approaches the boundary, or as either x or y approaches infinity. This means that the minimum cost has to exist at a critical point inside the boundary, and we only have that one critical point. So the box with the lowest cost will have dimensions of 1 meter by 1 meter by 10 meters. Now you get to try it. Pause the video and find the point or points on the cone z squared is equal to x squared plus y squared nearest the point P given by the coordinates 1, 4, 0. When you're ready, restart the video to check your understanding. We want to find the point or points on the cone nearest the point given with coordinates 1, 4, 0. I first need to understand exactly what I'm trying to minimize. I want to minimize the distance between the surface of the cone at XYZ and the point P at 1, 4, 0. We can do this by minimizing the square of the distance as well. So I'm going to let W be the square of my distance. W is given by the quantity x minus 1 squared plus the quantity y minus 4 squared plus z squared. But I already know that z squared is x squared plus y squared, so I can rewrite this as the quantity x minus 1 squared plus the quantity y minus 4 squared plus x squared plus y squared. Now I take the partial with respect to x of w. Wx gives me 2 times x minus 1 plus 2x. This gives me 2 times 2x minus 1 in simplified form, or x is equal to 1/2. The partial of w with respect to y gives me 2 times the quantity y minus 4 plus 2y. This becomes 2 times the quantity 2y minus 4, which gives me y is equal to 2. This means that there is one critical point at x is equal to 1/2 and y is equal to 2. At 1/2, 2, my z value becomes z squared is equal to 1/2 squared plus 2 squared. So z squared is 17 over 4, and z is plus or minus the square root of 17 over 2. There's only one critical point, but there are 2 points on the cone with a minimum distance to the point P given by coordinates 1, 4, 0. Those points are 1/2, 2, and plus or minus square root of 17 over 2. This should make sense because we know that my cone is going to be symmetric, so there is likely to be 2 points, one on either side, where I will see a minimum distance between the surface of the cone and the point P on the interior of the cone. Be sure and let me know if you have any questions about working with absolute extrema on bounded or unbounded regions.